Good morning and most welcome to 1304, and we will continue with Smolin's A Landscape Problem, and then I will add of action perception, which is the take from the body, so to speak, going into the same direction and having a lot of incredibly interesting parallels. It seems that the science of cognition and physics have encountered the same problem, although at different times. So I left off at page 9 in A Perspective on the Landscape Problem by Smolin. This is where I will continue. Sorry about this. We experience this great coldnesses here in Sweden, and with coldness comes the common cold. I'm so sorry about that, but I don't think I'm exaggerating if I say that 30% of Gothenburg now is suffering from some sort of cold. It's very common. Background independence, that is a very important word. As a consequence of the last principle, which is no unreciprocated actions, there should be no entity which acts on dynamical degrees of freedom, which is not itself a dynamical degree of freedom, which is acted back in return. This principle was used by Einstein to motivate his rejection of absolute space in favor of a theory general relativity in which the geometry of space-time is a dynamical degree of freedom. Another way to say this is that there must be no absolute or ideal entities whose properties influence the evolution of degrees of freedom, which are themselves not dynamically determined. Background independence. As a consequence of the last principle, we must rule out proposals for quantum for a quantum theory of gravity, which are dependent for their formulation on fixed, non-dynamical, classical geometries. This rules out as a fundamental perturbative formulations of quantum gravity and string theory. These must be approximations to background-independent formulations in which geometry is fully dynamical and fully quantum. So, to put it short, the present quantum mechanic thinking is to put everything on a fixed landscape of classical determinism, so to speak, projecting quantum mechanics into a grid, a matrix. This is the brilliance of Smolin. This is the absolute brilliance of Smolin. How could anyone discover that? This is a sharpness of his head that is just beyond me. The demand for an explanation for the choices of laws and initial conditions is deeply related to the requirement that theories of gravitation and space-time be background independent. Both demands reflect the need to explain the universe only in terms of dynamical processes internal to it. Both reflect the need that a scientific explanation for the laws and initial conditions of our universe not rest on conjectures that are beyond experimental check. There must be no fixed background geometry for space and time. For the same reason, there can be no fixed, timeless laws. Either would leave us with a description of the universe failing to test of sufficient reason. This connection is one link between the landscape problem and the problem of making a background independent formulation of string or M theory. What kinds of explanation count as sufficient reason in science? What kind of explanation can count as sufficient reason for a law or a theory? As I argued before, two general kinds of explanations that could be advanced to account for a state of affairs. Reasons can be logical or they can be historical. They both may serve, but they have very different consequences for the methodology of science. This is because logical explanations can be complete, while our knowledge of the past is always incomplete. This raises the question of whether we can ever give the complete sufficient reason for a feature of the present world, whose explanation has an historical component. Even if our knowledge of past conditions is detailed enough to justify giving a sufficient reason for a present fact in terms of conditions at some past time, there remains the problem that a complete explanation would involve us explaining those past conditions. So causal explanation can often involve us in a regress in which we just push the mysteries deeper into the past. It might be thus objected that sufficient reason is too strong of a criteria to apply to explanations in science. It rarely happens that we know enough about nature to give the complete reason for something has a given property rather than an alternative. Explanations in science is almost always tentative for two distinct reasons. Scientific explanations are always subject to revision when knowledge advances. Scientific explanations are also involved in the replacement of theories by newer theories, which explain the same evidence in different terms. As technology and science advance, we also learn more about the past. How are we to reconcile the demand for sufficient reason with the tentative character of explanation in physics? We do so by acknowledging that our attempts to give sufficient reason for present features of the universe, including the laws, may in many cases be incomplete, but we can still be faithful to the demand for sufficient reason by accepting explanations that leave room for further developments that may improve our understanding of the past. There's no shame in explaining the plenitude of galaxies in the universe in terms of postulating initial conditions shortly after the initial singularity, so long as we leave open the task of explaining those initial conditions. This is the case if we postulate that the initial singularity postdicted by classical general relativity was in reality a bounce from an earlier epoch. By doing so, we invite the possibility of explaining those initial conditions as being the result of evolution through the bounce. It is, on the other hand, against the spirit of the demand for sufficient reason to adopt explanations for present conditions that close off further inquiry. We do this if we adopt an a priori principle which posits that the inferred initial conditions are the result of a unique initial state of the universe. The problem with this may be that the principle is not subject to falsification or further verification, because it is alleged to only act once at the beginning of the universe. An a priori principle which is designed to postdict the initial conditions inferred from experiment without making any additional predictions cannot be falsified. The adoption of this kind of explanation stops further inquiry, so it is against the spirit of the demand for sufficient reason. This concern is addressed by the principles of causal closure and no unreciprocated actions. If all chains of explanation remain within the universe and involve only dynamical degrees of freedom that have reciprocal interactions with everything they influence, then our explanations of the present will go on only so far as our knowledge of the past. We call this the practice of modesty about past causes. Do not assert an untestable hypothesis that closes off further investigation, where a confession of ignorance leaves the situation open to genuine explanation when our knowledge of the past improves. To summarize, in some circumstances, the demand for sufficient reason must result in a confession of ignorance. When causal chains are pushed back into the past to the point where our present knowledge of past ends. This is better than proclaiming first movers or initial states, which are not subject to further explanations in terms of their past, and so cannot be further improved as our observations of the past improve. We can illustrate this principle of modesty with one of the main choices that face contemporary cosmologists, which is whether to accept the initial cosmological singularity as a first moment of time, or hypothesize that in the correct physics the singularity will be replaced by a bounce that opens up a much older past to scientific investigation. By endowing the very early universe with the past, the hypothesis of a bounce makes the unusual conditions of the universe explicable in terms of its prior history. If one instead hypothesizes that the initial singularity at the beginning of time one is face to face with the necessary of basic science on an inexplicable choice, which is the initial conditions of the universe. The full scope of the landscape problem. To emphasize the full import and scope of the landscape problem, we have to dig a bit deeper. As I will now argue, its roots lie in assumptions physicists have made since the time of Newton about the structure of physical theories. Newtonian mechanics, field theory, general relativity, and quantum theory have a common framework which is organized as follows. We specify a system to be studied. This is almost always an approximate or effective description of a small subsystem of the universe. We do this by specifying the degrees of freedom we are interested in studying. 2. We specify oh my God. Sorry about that. We specify a timeless space of states, C, which is a phase space or Hilbert space. This gives us possible initial states in which our system can be prepared. We specify a dynamical law acting on C. This allows us to evolve states in C, so that given the choice of initial state, prepared at an initial time, we can compute the state at any future time. We call this framework of theories the Newtonian paradigm. Because this framework has been so successful when applied to the small subsystems of the universe, it appears almost obvious that when we come to the task of developing a cosmological theory, we should just scale it up to include the whole universe in the state space C. However, as successful as it has been, this schema for physical theories cannot be applied to the universe as a whole. There are several distinct reasons for this. One, the Newtonian paradigm takes the dynamical law as input. It cannot be the basis of explaining why that law is the one that applies to our universe. Hence, to adopt this paradigm as a framework of a cosmological theory, we leave a great deal of mystery in our understanding of the world. We will fail to fulfill the demand to give sufficient reason for every cosmological question. Similarly, the Newtonian paradigm takes the specification of the initial state as input. Yes, this is true. It cannot justify or explain the choice of initial state. The demand for sufficient reason will again not be answered. 3. The Newtonian paradigm assumes that there is an absolute distinction between the role of state and the role of the dynamical law. This distinction can be operationally realized on small subsystems because we can prepare a system many times in different initial states and observed what aspects of the resulting evolution are universal and what are the consequences of the choice of initial state. The dynamical law is inferred from observations of universal features of the motion which are independent of the choice of the initial state. When we come to the universe, there is only a single history. And so we have no way to operationally or experimentally distinguish the role of the law from the choice of initial state. This can be a practical as well as a theoretical issue, because there can be degeneracies in cosmological models arising from the fact that a single observation can be explained equally well by modifying the law of motion or the choice of initial conditions. One sees examples of this in attempts to fit inflationary models to data such as the possible non-causalities. Any theory formulated in the Newtonian paradigm will have an infinite number of solutions. But the universe is unique. So only one cosmological history is physically real. The Newtonian paradigm is then very extravagant when applied to cosmology, because it not only makes predictions about the future of the one real universe, it offers predictions for an infinite number of universes which are never realized. The Newtonian paradigm cannot explain why the one solution that is realized is picked out from the infinite number of possibilities. Because of these issues, it is best to think of attempts to construct an exact cosmological theory by scaling up the Newtonian paradigm as fallacious, because they take a method that is very well suited to describing subsystems of the universe and apply it beyond its realm of validity. This can be called the cosmological fallacy. Note that this does not apply to commonly studied cosmological models, such as the standard cosmological model, as these are explicitly based on truncations to a subset of the degrees of freedom, namely the homogeneous degrees of freedom and small fluctuations around them in a limited region. One way to express the cosmological fallacy is through the following cosmological dilemma. The Newtonian paradigm expresses the forms of all the laws we know, which have been thought of as exact. Nonetheless, every law formulated and verified within the Newtonian paradigm can only apply to a bounded domain, and hence is approximate. Here is the argument for this perhaps counterintuitive assertion. To operationally realize the distinction between laws and initial conditions, one needs many instances to apply the law to. Only that way can one show that the law holds when the initial conditions are varied. But since there are many instances, each one is only a part of the history of the universe. Hence, each instance is a description of a subsystem of the universe. However, there are no true isolated systems in nature. Each treatment of an isolated system is an approximate truncation of an open system. Hence, each such theory is approximate. Only a truly cosmological theory could be an exact theory. But our different arguments tell us that we can only hope for sufficient reason within a cosmological theory that does not fall into the Newtonian paradigm. If one ignores the cosmological dilemma and proceeds to try to construct a theory of the whole universe within the Newtonian paradigm, one is committing the cosmological fallacy. The landscape issue is then an aspect of the failure of the Newtonian paradigm to serve as a basis for a truly cosmological theory. If we are to solve the landscape problem and not fall into an infinite regress, we must do so in a new framework which cannot be characterized as within the Newtonian paradigm. The task is then to invent a new theory which can be applied to the universe as a whole, which will not leave us asking why this theory and why these initial conditions. How can we do that? By seeking theories which transcend the three absolute features of the Newtonian paradigm. One, that the space of states is timeless. Two, that the choice of laws is timeless. And three, that there is an absolute distinction between laws and states. These comments apply to any theory expected to hold at the cosmological scale. Hence, they apply to the background independent framework from which it is hoped that different perturbative string theories will emerge. Hence, we learn something important about the search for the M theory. It must not be describable within the Newtonian paradigm. If it is to be a real theory of everything, it must be formulated in such a way that we cannot further inquire as to why this law and why these initial conditions. It must somehow furnish its own sufficient reason. Cut it short, the reasons for the universe have to be within the universe, not outside of it. Chapter 3. Options for a solution to the landscape problem. Yet another way to state the landscape problem is to assert that our observable universe does not contain enough information to answer the two big why questions. Why these laws and not others? And why those initial conditions? But if we insist on the principle of explanatory closure, then the universe must contain enough information to answer any query that can be made about its properties, including these two questions. The answer must lie in regions of the universe that we have not so far observed directly. For it is likely that the universe is bigger and older than the region we can observe. In our analysis of the why these laws question, we concluded that laws must have evolved dynamically to be explained. This implies that there were dynamical processes in our past by which the laws evolved, as we do not see any evidence that the fundamental laws or their parameters evolved in the observable past. These processes must have gone on in regions yet unresolved observationally. This accords with the intuitive picture that the effective laws may have evolved in events that involve energies or energy densities much in excess of those in our observable universe. We now face several choices. One, was there a bounce or singularity to our past? Two, did the evolution of laws happen all at once, or incrementally over many stages? That is, do we live in a first-generation universe, or does our universe have a long chain of ancestry? Three, was the chain of ancestry linear, so that each universe gives rise to a single progeny? Or does it branch, with each universe giving rise to many progeny? Take a short pause here, sorry. Let us investigate the different options. These give rise to three classes of global cosmological scenarios. Three options for global structure of the larger universe. If we posit that the initial singularity was really the first moment of time, then there is a brief time available for the evolution of the laws to have taken place. In this case, there is unlikely to have been time for incremental evolution through many epochs. Our universe then probably arose from some primordial state in one or few steps. One early suggestion for such a cosmological setting for variation of the laws was Vilenkin and Linde's eternal inflation scenario, within which an infinite number of universes are born as bubbles in phase transitions from a primordial, eternally inflating medium. In the simplest version of this framework, our observable universe is one of an infinite number of universes, each produced in a single step from a primordial state of eternal inflation. It is also possible that there are bubbles within bubbles, but these chains of descent are not taken as central to the explanatory power of the scenario as they are in cosmological natural selection. The resulting multiverse scenario posits that the infinite numbers of universes are mostly causally disjoint. We call this a pluralistic cosmological scenario. Although eternal inflation was proposed before the realization of the string landscape, it has become the setting in which much research on dynamical evolution of laws on the landscape has been carried out. On the other hand, by positing that the singularity was replaced by a bounce, we endow our universe with a deep past during which there may have been many epochs of classical universes. These would have allowed the effective laws to evolve incrementally over many generations, all in our causal past. These may be called cosmological scenarios with succession. There are again two choices, depending on what bounced. The Big Bang may have followed a complete collapse of a prior universe. So we arrive to the scenario of a cyclic universe. The big crunch of a cyclic universe may have given rise to a single progeny, or it may have given rise to many. The latter may be the case if there is a selection effect whereby regions of the crunch must be sufficiently homogeneous to bounce. Hence, we have to distinguish between linear cyclic cosmologies in which a universe has a single progeny and branching cyclic cosmologies in which there will be many. The other possibility was that the Big Bang was the result of the bounce of a black hole singularity. If black hole singularities bounce, then a universe may have many progeny, each the result of a collapse to a black hole. Indeed, our universe can be estimated to have at least 10 billion black holes, and hence at least as many progeny. Hence scenarios in which black hole singularities bounce are branching cosmological scenarios. The scenario of bouncing black hole singularities is the setting for the framework of cosmological natural selection, which will be discussed below. The only kinds of singularities which are generic in solutions to the Einstein equations are cosmological and black hole singularities. So these are the only options for cosmological scenarios in which singularities are replaced by bounces. So we have the following options for a global cosmological model. 1. Pluralistic scenarios such as eternal inflation, in which there is a population of universes, all derived from a primordial state by a one-stage process, largely, if not completely, causally distinct from each other. The second, linear cyclic scenarios, in which there is a succession of universes, each with a single parent and a single ancestor. 3. Branching scenarios, in which each universe has a single parent but many progeny. We now investigate the options for explaining the selection of laws in our universe in each of these three kinds of scenario. 4. Prospects for a solution of the landscape problem in the three scenarios. Before we analyze the possible solutions to the landscape problem offered by the three kinds of scenarios, we should be mindful of a few key issues. 1. In any landscape scenario, whether in biology or physics, there are two landscapes. The landscape of fundamental parameters and the landscape of parameters of effective low energy theories. There can be a rather complicated relationship between them. In biology, these are the spaces of genotypes, the actual DNA sequences, and the space of phenotypes, the space of actual features of creatures that natural selection acts on. In physics, these may be the landscape of string theories and the landscape of parameters of the standard model. In biology as well as in physics, the explanatory power of a scenario depend partly on how well understood are the relationships between the two kinds of landscapes. The second, the bounces of very high energy processes, but there is evidence for a lot of fine-tuning at the level of the low energy parameters. How can the bounces then play a role in selecting for fine-tuning of the low energy parameters? We can observe, this is the third one, we can observe only what is in our past light cone. If a cosmological scenario posits an ensemble of universes outside of causal contact with our own, then we risk a situation where the characterization of the other members of the ensemble is free from check by observation, there is a great danger then of just making stuff up to get answers we want. The only way to constrain an ensemble of causally disconnected universes by observation is if there is a dynamical principle that makes it possible to deduce that every or almost every universe in the ensembles shares some property P, then an observation is not seen of P. It would falsify the theory. Mindful of these cautions, we can now examine what opportunities are three kinds of cosmological scenarios offer for a solution of the landscape problem. Linear cyclic models. The linear cyclic models have a great advantage over the two other scenarios in that all the epochs or universes it posits are in the causal past of ours. There is then abundant opportunities for making predictions that are subject to observational check. So far, two kinds of cyclic models have been studied, and both offer falsifiable predictions. The ekpyrotic models of Steinhardt, Turok, and collaborators predict that there will be no observable tensor modes in the CMB. The conformal cyclic cosmology of Penrose predicts the existence of concentric circles in the CMB due to gravitational waves formed by colliding black holes in the previous era. What prospects then do the linear cyclic models have to explaining the selection of laws? One can easily hypothesize that at each bounce there are changes in the effective laws, perhaps brought about by phase transitions amongst vacua of string theory, or whatever the fundamental theory is. This will give us a series of points in the landscape representing the effective laws in each epoch. However, to explain the choice of laws, there must be an attractor in the landscape. Otherwise, the progression of laws through the epochs will just be random, and nothing about the present choice of laws will be explicable. For the evolution on the landscape to converge to an attractor, the changes in each generation must be small. Also, to explain the choice of parameters of the low energy theory by a series of transitions in the fundamental theory. It must be that small changes in the fundamental landscape give rise to small changes in the landscape of the low energy effective theory. Furthermore, that attractor must somehow be determined by properties of low energy physics. Otherwise, the tunings of the standard model will not be explicable. Branching models. Branching models share one good property with linear cyclic models, which is that there are long chains of descent. This can make possible incremental accumulation of good properties through slow, stable evolution to attractors. However, they deviate from linear cyclic models in giving rise to a growing population of causally disconnected universes. These can lead to predictions about our universe only to the extent that it can be predicted that there will be properties P shared by all or almost all members of the ensemble. This is illustrated by the two examples we have of branching models. Branching cyclic cosmologies. In the branching cyclic cosmologies, it can be hypothesized that only regions of the collapsing universe that are sufficiently spatially homogeneous will bounce to make new expanding universes. because the region must be very homogeneous to bounce. Each new universe will be very homogeneous. Homogeneity is then a property, P, that is shared by all members of the ensemble. Hence, it is predicated for our universe. One can hope that more detailed modeling of the bounces may lead to new predictions for our universe of this kind, which may be falsifiable. We can note that a great advantage of cyclic cosmologies in general is that they eliminate the need for inflation to explain the specialness of the cosmological initial conditions. Can the branching cyclic cosmologies explain the selection of the low energy physics? In this regard, the answer is the same as with regard to the linear branching cosmologies. The changes in both the fundamental and effective laws must be small from generation to generation. And there must be an attractor in the landscape of the low energy theory for the evolution to converge on. And now to Smolin's, I might say, own favorite. That is cosmological natural selection. Cosmological natural selection was invented to give an answer to the landscape problem that explained the reasons for the fine-tunings of the standard model without making use of the anthropic principle. The idea was to invent a cosmological scenario that naturally explained why the universe is fine-tuned for complex structures such as living stars, spiral galaxies, and organic molecules, using the same mechanism that biology uses to generate improbable complex structure. This suggested that there would be in cosmology an analog of biological fitness. The number of progeny of a universe as a function of its low energy parameters. This analogy inspired the suggestion that there would be an evolution of effective field theories on a landscape of parameters analogous to the fitness landscape. Studied by population biologists. This was inspired by an analogy between selection of effective laws in a cosmological setting and natural selection in a biological setting. The theory is based on two hypotheses. Universe reproduce when black hole singularities bounce to become new regions of space-time. During the bounce, the excursions through a violent interlude at the Planck scale induces small random changes in the parameters of the effective field theories that govern physics before and after the transition. The analog of biological fitness is then the average number of black holes produced in a universe, seen as a function of the parameters of the standard models of physics and cosmology. We can call this function of the landscape the cosmological fitness. Combinations of parameters that are local maxima of this fitness function are attractors on the landscape. After many generations, the population of universes becomes clumped in the regions near these local maxima. The great advantage of cosmological natural selection over linear cyclic cosmologies is then that it creates attractors on the landscape. This comes about because the effective laws which are most common in the ensemble of universes are those that reproduce the most. Which means they have the most black holes. Thus, a property P shared by almost all members of the ensembles will be, after many generations, the following: small changes in the parameters of the effective landscape will almost always lead to universes which produce fewer black holes. Another way to say this is the following: if we define the fitness of a point in the landscape by the average number of black holes produced by the universe with those parameters. Then, after many generations, almost every member of the ensemble will be near a local maximum of the fitness. This explains the specialness of the tunings of the parameters of the standard model, because it turns out that several aspects of those tunings enhance the production of black holes. These include 1. The large ratios required for the existence of long-lived stable stars. 2. The coincidences among the proton-neutron mass difference, electron and pion masses, making nuclear fusion possible, as well as the sign of the proton-neutron mass difference. The strength of the weak interaction, which appears fine-tuned both for nucleosynthesis and for supernovas to inject energy into the interstellar medium, catalyzing the production of massive stars whose remnants include black holes. 4. The fine-tunings which result in the stability and plentiful production of carbon and oxygen. These appear to be necessary to cool the giant molecular clouds from which form the massive stars, which are the progenitors of black holes, as well as to provide insulation to keep the clouds cold. It should be emphasized that cosmological natural selection is the only of our scenarios that explains the fine-tunings of the parameters of the standard model. It does so because the cosmological scenario makes low energy physics causative of structure on the vast scale, that of the population of universes. It does so by strongly influencing the distribution of parameters in that population. This feature could be mimicked by the branching cyclic models, but only if there were some reason why having something like our present low energy physics could lead a universe to have more regions which were sufficiently homogeneous to bounce. This is unlikely because the conditions in the final crunch are not going to be sensitive to details. To details of the choices of parameters of low energy physics. What cosmological natural selection accomplishes, apparently uniquely, is to make the population of universes delicately sensitive to the parameters of low energy physics. It does this naturally and necessarily because it takes delicate tunings of parameters to produce a large numbers of black holes. Because of this coupling between cosmology and low energy physics, cosmological natural selection makes a few predictions that are vulnerable to falsification by present observations. It is instructive to review 3 of them. To maximize the number of black holes produced, the upper mass limit, the UML, for stable neutron stars should be as low as possible. As pointed out by Brown and collaborators, the UML would be lower in neutron stars containing kaon condensates in their cores. This requires that the kaon mass and hence the strange quark mass be sufficiently low, since none of the other physics leading to black hole production is sensitive to the strange quark mass. Cosmological natural selection then implies that the strange quark mass has been tuned so that neutron stars have kaon condensate cores. Both the theoretical understanding of nuclear physics of kaon condensate cores and the observational situation has evolved since this predication was established in 1992, some time ago. Bethe and Brown argued that the kaon condensate neutron star would have an UML to the value of 1.6 solar. So that is the figure I used initially. However, as emphasized recently by Latimer and Prakash, there is actually a range of predictions for the UML kaon. These depend on assumptions about the equation of state and range upwards to 2 solar masses. So in the light of the current knowledge, the correct prediction is that 2 solar units are needed for the UML. The present experimental situation is summarized further below, but there is an observation of a neutron star with a mass of 1.9 solar masses to good accuracy. This is just inside the range consistent with the prediction that neutron stars have lowered upper mass limits due to having kaon condensate cores. However, there are observations of neutron stars with wider error bars around 2.4 solar masses. This, if confirmed, would be inconsistent with the prediction of cosmological natural selection. One question often raised is why cosmological natural selection is not ruled out by the possibility of changing a cosmological parameter to greatly increase the production of primordial black holes. This could be done by turning up the scale of the density of fluctuations, which has been measured to be around 10 up to -5. The answer can be given in the context of a single field, single parameter inflation. In that theory, delta is determined by lambda, the strength of self-coupling of the inflaton field. This controls the slope of the inflaton potential, and hence the numbers of if e-foldings grows with the decreasing lambda. This means that the volume of the universe, and hence the number of ordinary black holes produced, scales as V almost to the equivalence of E up to N. Note finally that the choice of initial conditions is not so far explained by the scenario of cosmological natural selection. This is challenging as new universes arise from black hole singularities, which are generically very inhomogeneous. Thus, cosmological natural selection probably requires inflation to make sense of the specialness of the initial conditions. Pluralistic cosmological scenarios. Let us finally turn to the pluralistic scenarios, of which eternal inflation is the main example. In this scenario, an infinite population of universes is produced in one step from the formation of bubbles in an eternally inflating primordial phase. At least in its simplest form, this lacks the strengths of either the cyclic or the branching scenarios. While a few other bubbles may have collided with our universe, giving a chance to confirm, but not actually falsify predictions of the scenario. Almost all the universes in the population are causally disconnected from our own. It is usually assumed that the universes that are created randomly sample the points in the landscape of the fundamental theory, so there are almost no properties common to all universes. The only property P put forward as satisfied in all universes is that the curvature should be slightly negative. However, this would be difficult to confirm or falsify with the near future observations, because it will require a great deal of precision to distinguish this from vanishing curvature. Excuse me. Moreover, the formation of bubbles takes place at very high energies. Typically, grand unified scales where the details of the parameters of low energy physics are not going to matter. So there is no mechanism for coupling between the fine-tunings of low energy physics and the dynamics that produces the ensemble. in its absence, it has to be concluded that universes like ours, with fine tunings of low energy parameters, are very rare. In the absence of any large set of properties P, common to the ensemble proponents of eternal inflation, have to fall back on the anthropic principle. This has so far not led to any genuine predictions, and it's pretty clear why this is unlikely. The properties of a universe can be divided into two classes. The first class consists of properties that play a role in making a universe friendly to life. Examples include the values of the fine structure constant and the proton-neutron mass difference. Class 2 consists of properties that do not strongly influence the biofriendliness of a universe. These include the masses of the second and third generation fermions. The first class of properties must hold, and their verification does not provide evidence for any cosmological scenario, because we already know the universe is biofriendly. That is to be explained by an argument that is not circular, that is, does not assume our existence. The second class are assumed to be randomly distributed in the ensemble. Hence, since they are uncoupled to biofriendliness, they will be randomly distributed in the ensemble of biofriendly universes. Hence, no predication can be made for them. These kinds of arguments, developed in more detail, make it very unlikely that the anthropic principle can ever be the basis for a prediction by which a cosmological scenario could be falsified or strongly verified. What are we to make then of the claims that there have been successful predictions made based on the anthropic principle? In fact, such claims must be fallacious, and they have been shown to be. This is discussed in detail, but I can mention quickly here that there are basically two kinds of fallacies in these claims. First, a statement that X is essential for life is added to an already correct argument involving X. For example, Hoyle argued successfully that if carbon is produced in stars, there must be a certain energy level in a nuclei. He based his successful argument on the observation that carbon is abundant in the universe, the fact that carbon plays a role in life plays absolutely no role in the argument. Later, Weinberg argued that if there were to be an ensemble of universes with random values of the cosmological constant, that lambda would be seen to have a value within an order or two of magnitude below a critical value. Lambda 0 above which no galaxies form. This had nothing to do with life, as galaxies are observed to be plentiful. It is true that the observed value came to within 5% of the lambda 0 Weinberg used. So that would show to be the death toll of the anthropic principle. So what they do, they use arguments that includes life, like carbon dioxide and organic chemistry, to prove that this universe is this universe. So it's a trickery, and obviously Weinberg himself were not aware of this, and neither were Hoyle. And we must remember that the anthropic principle is what drives the current fallacies. It's very, very important. I did not realize that before I started reading Smolin. And there was even a time where I liked it. And we must remember Stephen Hawking was a great admirer of the anthropic principle. And so was Carl Sagan, and I would say the absolute majority of physicists today. It's a necessary requirement to rule out every other universe and every other classical law, any other initial conditions. It all circles on the anthropic principle. Why is the universe fine-tuned for us? This could be reversed into saying, we are here, and therefore we have fine-tuning. Very, very trickily thought of thinking. It's a fallacy, but how to realize that? Oof, that is tough. I end off now. I say thank you very much for listening. Have a very pleasant afternoon. Bye-bye for now.